after.
Okay,
Yes,
thank you.
sir.
So yesterday we have seen up to the direct sequence spread spectrum BPSK signal generation. So we have gone through the block diagram of the DSSS transmitter. I hope up to this point we have covered, and we have seen that the empty signal, that is the transmitted signal, that is nothing but the PN sequence signal CT as well as the basic signal BT is there. Now that signal would be passed through the channel, and in this channel there would be added some interference noises, that is IT is added here. So up to this point we have covered, that is your equation number 4 is there, 3 and 4. Now we have to be move, and we have to be see that up to this waveform also we have seen, that is the first one is the data signal BT, and then it would be mixed up with the spreaded code, that is PN sequence, that is CT is there, and further the resultant signal MT has been be generated, that is a product of the BT and CT. Okay, so now this MT signal, that is a transmitted direct sequence spread spectrum signal, has been transmitted into the through the channel, and when it would be received by the receiver, this is the structure of the DSSS receiver or decoder circuitry. So in this circuitry you can see that the received signal RT is received here, that is nothing but the summation of the MT plus IT, that is interference signal, and again we have to be use a locally this particular signal has been be again would be mixed with the locally generated PN sequence, that is CT is there. So local PN code generator would be used here, and that would be used to generate the signal ZT, that is a product of again RT and CT. So in this particular case we have to be after the product of this multiplier or product modulator is a signal ZT, that is nothing but RT into CT is there. Then it would be passed through an integrator. So integrator having the limit 0 to TB, that is a bit period, and then a voltage signal V is generated, and where we have to be compare the this signal is either greater than or less than the threshold value, that is 0 is set here. If it is greater than 0, then it is 1, and if it is less than 0, that means 0 data is received. So in this way we have to be recover or decode the binary data 1010. So you can see the equation number 5 is here, that is ZT, that is nothing but CT into RT. CT is, again I am saying, it is locally generated PN sequence, that is the exact replica of the PN sequence generated at the transmitter end. Then when you have to be put up the value of RT on the equation number 5, you would be got the new value of the ZT, that is in terms of CT and BT. So we have to be substitute the value of RT, that is MT plus IT is there. So we have to be again got this value. Okay, MT is what? CT into BT, that is would be used here and to generate the equation number 6. So this is the output of the product modulator ZT, and this signal would be further passed through an integrator, and whatever the signal that we have got in the case of the ZT, that is CT into IT, here we have substitute the value of C square T as 1, because this is the repeated sequence is there, and when the same term would become square would be considered as a 1 is here. So this is here. CT is basically a PN sequence, so it is having a wide bandwidth. Okay, and IT is a noise or interference signal. So the product of CT IT is also a very wide bandwidth signal is there. So this wide bandwidth signal is large. The bandwidth of CT IT is very much large as compared to the baseband signal BT. So what happens? The signal ZT is then passed through an integrator that would be integrated the signal over 1 bit period, that is TB, and this integrator would be act as here a low pass filter. Means it would be remove the wideband noise CTIT. It would be only pass the low frequency baseband signal. So in this way, we have to be get a baseband signal at the output of the integrator, and that is in terms of voltage signal V. And the decision device would be now compare this V with the threshold set is here, that is 0. If V is greater than 0 means we have received the binary 1. If we have less than 0, it would be means we receive the binary symbol 0. So this is the simple way that we have to be use a receiver is here. So this is again I am showing the DSS with the coherent BPSK here. So in this case only what we have done, binary data sequence is passed through a polar non-return to 0 encoder. Again we have used here PN sequence. In the previous case we have used only the DSSS, but now we have to use the coherent BPSK with it, along with it. So what we have to be do after this spreading of the signal. Spreading of signal means we have to be the output of the product modulator where we have added a multiply a PN sequence along with the data signal, that is empty. This empty signal, that is wide bandwidth signal, would be now passed through a binary PSK modulator, and with the help of some carrier signal, that is high frequency carrier signal is there. Finally we have to be got a signal that is XT, that is the output of this DSSS coherent BPSK. So this signal would be transmitted through the channel. So here you can see that, please take the screenshot of this block diagram of DSS with the coherent BPSK. Now the transmitter uses two stages of modulation. In the first stage we have to know the product modulator where we have to be multiply the data signal with the PN sequence BT and CT, and in the second stage we have to use a BPSK modulator. So output the product is XT. It is a nothing but a direct sequence BPSK signal. It is a DS BPSK signal. Before this, in the unit number 5 we have seen only the BPSK. Now it is a direct sequence BPSK. So the bandwidth of DS BPSK is very much higher as compared to the normal BPSK signal. Now you can see here the MT we have already defined, that is CT into BT, that is the input, one of the input of the binary modulator, BPSK modulator. So MT is here, what is it? Is the NRE, not return to 0 signal, and having the amplitude of +1. So it is multiplied with the BPSK carrier, and finally we have to be got the BPSK carrier. We know that it is the orthogonal carrier, so it could be defined as a square root of 2PS that sine 2 pi FCT. FC is the frequency of the carrier signal that we are used here. So here you can written it as equation number 1. The carrier is equation number 2. Finally, the output of this is XT, that is the product of MT and the phi t. So finally, we have to be got MT into square root of 2PS sine 2 pi FCT, and this would be given as the equation number 3. Okay, so this is your equation number 3, that is defining the BPSK DS BPSK signal, that is direct sequence BPSK signal, that is XT. Now this signal would be passed through a carrier, and we know that the DS BPSK signal XT is here having the you can say the two phase shift is one of the two values, that is either it is a 0 or pi. So the phase shift would be 0 to pi, and the polarity of the data sequence would be and the PN sequence would be maybe opposite. So you can see here MT would be ±1, we know that, and then XT is also plus minus because its phase would be vary between the 0 to pi depending upon the polarity of the PN sequence at the time t. So if PN sequence is positive, and on the same time if beta signal is also positive, so phase shift is 0. If both are in opposite polarity, then phase shift is 180 degree. So depending upon the polarity of the data signal and the PN sequence, the total phase shift of the XT would be decided. Okay, So in this way, we can define the DS-BPSK signal. Now, this signal would be when passed through the channel and then it would be received by the receiver. We have to see the receiver structure of this. Before this, we can also see the waveform. You can see here very simple waveform I have shown, that is MT, that is a combination of the BT, CT, that is again an NRZ signal, but high bandwidth signal is there. Then it would be mixed up with the carrier signal that is having the phi T, and then whatever the signal that is XT is generated, that is having the phase shift of either 0 or 180 depending upon the polarity of the signals in the case of MT. So finally we have to be got this DS-BPSK signal. Now you can see the receiver structure of this DS-BPSK receiver. So it is a diagram. You can also note it down this diagram. This is nothing but your DS-BPSK receiver structure. Okay. So in this case of DS-BPSK receiver, again whatever the received signal, it is considered as here, and this received signal would be YT is why it is some noise would be added in the transmitted signal. Then again we have to use because it is a coherent detector, we have to use a local carrier generator. So it would be having the same carrier signal phi that we have used in the transmitter side. So finally we have to be generate a signal out of this product modulator that would be passed through a low pass filter. So it would be the output of the low pass filter is M cap T. This signal would be now again product mixed with the PN sequence that is generated by the local PN code generator, that is nothing but a replica of the PN code generator that we have used in the transmitter end. So again, whatever the output would be there of this product modulator, this would be integrated through integrator, that is nothing but a filter, and then it would be generate the output signal V. Again, it will be passed through a decision device that is having the threshold, and if it is threshold is the signal V is greater than this threshold value 0, then it is the binary 1, and it is less than 0, it is the binary. So see here, DSSS signal and DS-BPSK signal system is nearly same. Only the difference we have used the BPSK modulation technique. Rest of the things are nearly same is here. Okay. So we have to be see the important terms that we have to be remember when we have to be learning this DSS, direct sequence spread spectrum system. The first important term performance parameter is the processing gain. So what is the formula of processing gain? Processing gain is nothing but bandwidth of spreaded signal and upon the bandwidth of unspreaded signal. Okay. So processing gain, actually it is the gain achieved after the process of the spread spectrum technique over the unspreaded signal. So here you can see the bandwidth of unspread data signal means unspreaded signal. So what is the bandwidth of this signal is? It is 1 upon bit period 1 upon TB. That is you can also say the RB is there. Then bandwidth of the spreaded signal, that is 1 upon TC. Here not TB, it is a chip time TC. So TC is what? It is a chip time is there. We have learned the chip in the last lecture. So processing gain is now 1 upon TC upon 1 upon TB means TB upon TC. This is the processing gain, or RC upon RB. Okay. So in this way you can define the processing gain, that is nothing but it represents the gain achieved by the processing after the processing of the spread spectrum signal over unspreaded or data signal. Okay. So this is also one of the important parameter of performance of DSSS system. Second one is the performance parameter is probability of error of direct sequence BPSK system. Okay. So if you have to be see that the expression for the probability of error of the coherent BPSK signal is PE is 1 upon error function. ERFC means it is error function. That is square root of the EB N naught. EB is what? It is energy of the bit, and N naught is the average noise power. So it is average, it is the ratio of average signal to noise power. Okay. So it is 1 upon error function of EB into JTC. So J is what? It is average interference power, and TC is the chip time. So generally TB is equal to n times of TC. Okay. So here JTC is mentioned as a average noise or interference power is here. This is the second performance parameter of the DSSS system. And the third one is that is the main purpose of this spread spectrum technique, that is jamming. So it is a capability of the jamming the signal. So the jamming margin could be also find out, that is anti-jam characteristics actually. So J is what? J already we have defined, it is the average interference power with respect to the signal power PS. It is considered as a jamming margin, the ratio of J upon PS. So that is equal to processing gain upon EB upon N naught, signal to noise ratio. So J upon P is the called jamming margin. The jamming margin and its ratio, it is the ratio of average power of interference to the average data signal power. So it could be represented in terms of dB scale. So it would be PG in dB scale minus EB upon N naught in dB scale. So jamming margin in the dB would be nothing but processing gain in decibel scale minus 10 log 10 EB upon N naught, average signal to noise ratio. Okay. So these are the three important processing parameters of the DSSS system. Now that sometimes the numerical would be asked on these three parameters. So you have to be remember the formula as well, so that you have to be solve the numerical. Application of the DSSS signal systems. So it is used in the anti-jamming of the signals. It would be used for the low probability intercepting. It would be used the CDMA technique, code division multiple access. It is used for the ranging or using the direct sequence spread spectrum technique. So after the application, we have to go for the second kind of the spreading signal, that is frequency hopping. So frequency hop spread spectrum signals, FHSS. So the capability of DSSS system to visit intentional interference, or that is called the jamming, is depending on the processing end. Generally, we know heard about the jamming of the signal. Sometimes you have generally see it when the counting of after the election is there. So in the office where we have to count the votes, so there we have to use the jamming of the signal. So if there in the electoral office, we have to use a jammer to jam the external communication signal, so that whatever the person sitting inside that particular hall, that would be not able to contact with their friends or the neighbors or the known person outside that particular hall, so that there is a probability of error would be less. Okay. So this kind of the application, we have to use the jammer. So it would be done with the help of either DSSS sequence system or frequency hop spread spectrum system. So the capability of DSSS system would be depend upon the how much it is capable of for facing the intentional interference, and it would be depend upon the processing gain of that particular DSSS system. Okay. Now, but the capability of the physical devices used for the generation of PN sequence put physical limitations on the maximum value of the processing gain. So hence it would be capability to combat the jamming would be obstruct. So under such conditions, an alternative system could be used, that is called the frequency hop spread spectrum. Wherever the DSSS system would be fails, we have to use the FHSS system, frequency hop spread spectrum system. So frequency hopping means what? Transmit the data bits in different frequency slots. In this case, we have to not use a single frequency. We have to use a different frequency slot where we have to transmit the data bits. So the total bandwidth of the output signal is equal to the sum of these frequency slots or frequency hops. So thus, in the case of FHSS, carrier frequency hops randomly from one frequency to another. Means it will be switching from one frequency to another frequency So it is very difficult to determine which particular frequency is used at which time. It is very difficult to hack the signal, or it is very difficult to jam that signal. Okay, and in this case we have generally used the MRE FSK signaling technique along with this frequency hop spread spectrum. So basically there are the two types of the frequency hop spread spectrum, that is low frequency hopping, and second one is the fast frequency hopping. So first of all, we have to learn about the slow frequency hopping. So in the slow frequency hopping, what happens? Normally, k successive bit of the input data sequence represent 2 raised to the power k, means m symbols, and those distinct m symbols are transmitted with the help of MRE PSK, FSK. Actually, it is not PSK, MRE FSK signal. Okay, so it is used the MRE FSK modulation system. Okay, so the spread spectrum carrier frequency hops randomly from one frequency to another. So we have to see what are the some important parameter of this low frequency hopping. First is hop rate, that is RH. So the rate of change of frequency hops is called hop rate. Symbol rate, second one. The rate at which the k bit symbols of the data input sequence are generated is called symbol rate. Okay. So these two are the very important parameters that we have to be remember during the analysis of this slow frequency hopping and the fast frequency hopping. Now we have to be see what is the definition of the slow frequency hopping. When several symbols of the data are transmitted in one frequency hop or one frequency slot, it is called the slow frequency hopping. This means symbol rate is higher than the hop rate. Well, means the number of signals would be generated that would be more than the frequency hop. So it is called the slow frequency hopping. So this is the basic structure of block diagram of the frequency hop MRE FSK transmitter. Please note down this diagram. So you would be found that in this case, first of all, binary data sequence BT is applied, and to the MRE FSK modulator, and then the output of this MRE FSK modulator is nothing but a MSFK signal is there, and this signal would be applied to a mixer block that is obtained from a digital frequency synthesizer. So the mixer consists of the multiplier followed by a band pass filter. So the input of the mixer is output of the MRE FSK as well as the output of the frequency synthesizer. And then the output of the mixer would be passed through the band pass modulator. So at the multiplier output, we get two input frequencies, and their sum and their difference as a frequency component. So the band pass filter is designed to select only the sum frequency and rejecting the all other components. So whatever the band pass filter is used here, that is used to detect, please note down this diagram simultaneously. This band pass filter would be designed to select only the sum frequency component and rejecting all other frequency components. And this sum component of the frequency is then transmitted. Okay. And if you have to see the successive k bits of the input binary data sequence will be from one symbol M. Such symbols can be transmitted using the MRE FSK system. So here M is nothing but M is equal to 2 raised to the power k. So MRE FSK modulator will be assign a distinct frequency for each of the M symbols. Thus, in this way, the frequency of the mixer input obtained from the MFSK modulator is changing continuously. So the other input to the mixer is what? It is coming out from the synthesizer, and the synthesizer output at a given instant of time is nothing but a frequency slot or frequency hop. And the input of the frequency synthesizer is what? It is output of the PN code generator. The successive bits of the PN code generator would be given to the frequency synthesizer, and the output of the frequency synthesizer is given then to the mixer. Each frequency hop is here mixed with the MFSK signal to produce the transmitted signal, and the frequency hops at the output of the synthesizer are controlled by the successive bits at the output of the PN code generator. So the output bits of the PN code generator changes randomly. We know that it is a random generator, and therefore the synthesizer output will be also changed randomly, and hence frequency hop will be produced or vary in random manner. If the number of successive bits at the output of the PN code generator is n, then the total number of frequency hop will be 2 raised to the power n. Okay, so in this way you can see that if the number of successive bits to the output of the PN code generator is n, means it would be frequency synthesizer will be generated 2 raised to the power n frequency hop signals are there. So total bandwidth of this particular transmitted FH MFSK signal is very large, in order of the some gigahertz. So this is all about the FH MFSK transmitter. Now that is same I have written in the slide. Now we have to see the receiver of the FH MFSK signal. So in the receiving signal, the transmitter signal would be passed through a channel, and then the received signal, and it would be received signal would be mixed again with the mixer, where we have to be again use the locally generated PN sequence generator and same frequency synthesizer that is we have used in the transmitter end. Okay, so we have to be, so due to the large bandwidth occupied by this FH MFSK signal, the coherent detection of this signal is possible with each hop. This is because for the coherent detection and the phase synchronization of the locally generated PN sequence locally generated carrier would be same as the carrier that we have used in the transmitter side. But the frequency synthesizer used in the FH MFSK signal receiver are unable to maintain this phase coherence over the successive hops. So therefore, most frequency hop spread spectrum system use the non-coherent A-Murray modulation schemes, because it is very difficult to maintain this phase coherence. So most of the time we have to use the non-coherent also. Okay, so here the receiver signal is applied to a mixer, and other input is coming out from the output of the frequency synthesizer, and therefore the output of the multiplier would be, we get two input signal frequencies, means the sum of received signal frequency and the frequency synthesizer frequency, and their difference of the signal frequencies are there. So both sum and difference signals would be generated, and that would be the output of the multiplier. Out of this summation and difference frequency component, the difference frequency component would be discarded, or this difference frequency component is selected by the band pass filter. Difference frequency signal is selected by the band pass filter, and that follows by the again another kind of the that follows by the multiplier actually. So this band pass filter is used here. So this difference signal is nothing but what? It is a MFSK signal. It is nothing but a A-Murray FSK signal. This difference signal is nothing but a MFSK signal. And thus mixer removes the frequency hopping. In the transmitter side, this will be band pass filter would be only pass the adding signal, summation signal, means frequency hopping signals. And at the receiver end, it will be discard the summation signal, only by the difference signal, that is nothing but a A-Murray FSK signal is there. So the MFSK signal at the mixer output is then applied to the non-coherent MFSK demodulator. So at the output of the MFSK detector, we obtain a digital modulating signal, that is nothing but a binary signal BT. Okay. So in this way, we have to be recover the signal at the output of this receiver. So the non-coherent, sometimes I have told you that we have to be able to maintain the phase of these two signals. So non-coherent MRE FSK detector can be also implemented as a bank of M coherent match filters. So each match filter is matched to one of the turns of the MFSK signals, and the larger output out of the M available output of the filters is selected to obtain a digital modulating signal. So this is the alternating arrangement you can also do instead of the coherent. So the important parameter of this FHSK MFSK signaling technique is chip rate. So first of all, we have to see that what is the chip rate. In the MFSK, the individual frequency of the smallest duration is called the chip duration or chip frequency. And then in slow frequency hopping, multiple symbols are transmitted per hop or per slot of the frequency. Means in a single hop, every symbol have independent frequency. That is, the chip rate RC is equal to the symbol rate here, because every symbol having the independent frequency. So for the slow frequency hopping, RC and chip rate is equal to the symbol rate RS, that is bit rate upon K, RB upon K, because we have used the K successive bits. So RB is the input bit rate and K is the number of bits or symbols that we have used for generating the spread spectrum signal. Okay. So in this way, we have to be calculate the chip rate also. That is also very important formula. Another parameter that we will be learn in the MFSK signaling is processing gain. So the processing gain is again defined as the bandwidth of the spreaded signal upon the bandwidth of the unspreaded signal. Here the bandwidth of the spreaded signal is 2 raised to the power n fs, and bandwidth of unspreaded signal is fs. So it would be finally 2 raised to the power n. N is the number of bits used in the PN sequence. So these are the two important parameters that we have to be learned in the case of frequency hopping spread spectrum technique, and that is all about the slow frequency hopping. Now we have to be little bit insight on the fast frequency hopping. So when the several frequency hops takes place to transmit one symbol, it is called the fast frequency hop. In the previous case, one frequency hop for per symbol, but here now multiple frequency hop for one symbol. That is called the fast frequency hopping. Therefore, the hop rate RH is higher than the symbol rate RS. So the fast frequency hopping is used for generally for defeating a smart jammer who tries to interfere the transmission. So before the jammer could understand the frequency band which is being to be used by the transmitter signal is happened to shift to the new carrier frequency. So in this way, it is very difficult for the jammer to detect the actual frequency on which we are transmitting the signal. And again, in this case, the chip rate, hop rate is basically higher than the hop rate of the, you can say, hop rate is higher. So the chip rate is equal to the hop rate. So RC is nothing but it is equal to RH. And RC is what? It is RB upon K. Here RH is, remember that one thing, RC is equal to RH, but RH is what? RH is greater than RS. Okay. So this is all about the frequency hopping spread spectrum technique. Generally in the examination, sometimes ask the description of this or sometimes ask the comparison between both of them, slow and fast frequency hopping. So you can write the table. I have not shown the table here. You have to be prepare that table. Like the slow frequency hopping where the multiple symbols are transmitted per frequency hop. In the fast frequency hop, multiple hops are taken to transmit per one symbol. Chip rate is equal to symbol rate in the slow frequency. In the fast frequency, chip rate is equal to hop rate, and hop rate is greater than the symbol rate. So that is also a relationship. Then the same carrier frequency used to transmit the one or more symbol. One symbol is transmitted with the help of the multiple frequencies or different hops. Jammer can detect the slow frequency hopping signal, but the jammer can't be detect the fast frequency hop signal is there. So these are some comparisons. So in the tomorrow lecture, we would be learn the access technique, multiple access technique or multiple random access techniques there. Okay, and that will be the last lecture of this unit and this subject tomorrow morning. Now we would be complete our practical also. So please put up your attendance here, and if the signal would be lost, so you have to be rejoin again, because practical would be take at least 10 minutes. So you do not need to give too much time, but at least rejoin this session if the time would be elapsed. Okay, so that we would be complete our practical of PN sequence. And also in the 3:15, all the T3 batch students would be joined for the tutor meeting. This is the last tutor meeting of this semester. Quickly, fast, fill up your attendance. Okay, thank you for this lecture. Now rejoin the session again. Only 10 minutes we have to be required to conduct this practical. So I am ending the meeting now, and not ending, but you have to be rejoin the new session.